In this video, we continue our study of higher order Cauchy Euler ordinary differential equations. This time we'll have an example, or we'll look at an example that has repeated real roots for that characteristic equation. So just as a refresher, a differential equation is Cauchy Euler if you have constants times x to some power times the derivative is each term, and then you're just adding those up, and then the sum is equal to 0. Now, if the order of the derivative is equal to the degree of that polynomial term that's multiplying it, or alternatively, if the power of x here is equal to the order of the derivative here, these match, these match, these match, all the way down. If that's true, then you're dealing with a Cauchy Euler differential equation. So you're going to let your dependent variable equal your independent variable raised to the mth power. And after you substitute, you're going to differentiate as many times as necessary and substitute. Your nth order differential equation will simplify into an nth degree polynomial equation in M. And you'll see that if y equals x to the m is the solution of the differential equation, then M has to satisfy this nth degree polynomial equation. So we're going to be looking for solutions m sub 1, m sub 2, all the way through m sub n. And those are the solutions to that characteristic equation. Now, if your differential equation has, or if you have distinct roots on this list, they're real numbers and they're different from each other, then you have k different solutions here if you have k of those. So x to the m1 is the first solution, x to the m2 is the next one, x to the m sub k is the next one after that, and those are all distinct real roots. Now, if you have a repeated root m, and it's repeated k times, then you have k linearly independent solutions. The first one is exactly what you would think it is. It's just y equals x to the m1. And then to get the next linearly independent solution, you just multiply by natural log of x, and that natural log of x would come from reduction of order. If you keep doing that, or you can keep doing that, multiplying by natural log of x as many times as necessary in order to get the number of linearly independent solutions that correspond to the number of times that that root is repeated. So let's say you've got this guy, that's your characteristic equation factored. Well, if that happens, m equals -1 is the root associated with this factor. Since that factor appears 3 times, we can think of m equals -1 as a root that's repeated 3 times. So we need 3 linearly independent solutions that come from m equals -1. The first one is x to the -1. The next one is x to the -1 times natural log of x. And then you take that and you multiply by natural log of x again to get the third solution. And then we do the same thing over here. That's a repeated root as well, m equals 2. So you get 2 solutions. First one is x squared, and the next one is x squared times the natural log of x. Now, if you have complex conjugate roots, those always come in pairs. If those pairs are repeated k times, you have 2k linearly independent solutions. Now, the first pair is this x to the alpha cosine of beta natural log of x and x to the alpha sine of beta natural log of x. Those are the first 2 linearly independent solutions if this was only repeated, or the factor only appeared once. But if it's repeated a number of times like this, where you've got that complex conjugate pair as the root, or the roots of this quadratic polynomial, and it's repeated 3 times, you actually have 6 roots associated with this. So the first 2 just involve the sine and cosine. It's x to the alpha times cosine of beta natural log of x, and x to the alpha sine of beta times natural log of x, where alpha is the real part and beta is the imaginary part of those complex conjugate solutions to that polynomial equation. To get the second pair, you multiply by natural log of x again. To get the third pair, you multiply by natural log of x again. And you do that as many times as necessary until you have k pairs, if that quadratic expression that has the complex roots is repeated k times. So if I have this repeated 3 times, I have 3 pairs or 6 linearly independent solutions. Okay, so that's what we're expecting, and this time we're going to do an example, and my hope is that I've written it so that this has repeated real roots as solutions. I actually couldn't find one in the differential equations books I have with me at the moment. I'm away from home, and I don't have all my Diffie books with me, so I had to make one up. Hopefully I made it up correctly so that the solution has repeated real roots. Okay, so this is our differential equation. And, oops, I forgot my x's. That's got an x cubed there and an x squared there and an x there. Now it's a Cauchy Euler differential equation. We've got the third power of x times the third derivative, second power of x times the second derivative, first power of x times the first derivative, and 18 times the 0th derivative. No x's there. So we see that it's Cauchy Euler. So we're going to let y equal x to the m. Compute the second derivative, or the first derivative, excuse me, using the power rule. So bring the power down, multiply by x to the 1 less power. Then here you want to do the same thing again, bring the power down, multiply by x to the 1 less power. If you distribute that m, you get this. Then you bring the constant down, bring the power down, multiply by x to the 1 less power, and it was a third order differential equation, so we only need the third derivative here. If you want, you can distribute here. First times first is m cubed, outer times outer is minus 2m squared, and inner times inner is another negative m squared, so we've got minus 3m squared there, and last times last is 2m. And so we've got that there. So we take these guys and we substitute into the differential equation. So we've got x cubed times y triple prime, which is this, minus x squared times y double prime, which was this. Don't forget your parentheses. Minus 6x times y prime, which was that, plus 18 times y, which is x to the m. That's equal to 0. So we substitute it into the differential equation. And then we will simplify. Now x cubed times x to the m minus 3, if you are multiplying those two together, remember when you're multiplying powers of x together, you add the exponents. That's going to give me an x to the m. And this x squared times x to the m minus 2, when I add those exponents, I get x to the m as well. There's an x to the first and an x to the m minus 1. We add those exponents, that's an x to the m, and then we have an x to the m over here. And then what's left over is the polynomial pieces that are left. So I've got m cubed minus 3m squared plus 2m. And then I'm subtracting this quantity. So I'll subtract m squared, and I'm subtracting a negative m, so that's plus m there. And then I'm subtracting 6m there and adding 18, and we're setting that equal to 0. Now, this times this is 0. If this is 0 or this is 0, now this is 0 and x equals 0, but we're looking for solutions, y equals x to the m, on some interval on the real line. So I'm not looking for x to be a particular value. I want this times this to equal 0 for a range of values for x. So if that's going to be true for a range of values for x, then the polynomial part must be 0. So let's simplify this polynomial. We've got m cubed here. And I've got minus 3m squared minus m squared is minus 4m squared. And I've got 2m plus m is 3m. 3m minus 6m is negative 3m. And then you've got that plus 18 at the end, and that equals 0. So this is your characteristic equation. Now from here, you want to come up with some way of factoring this. Now this one doesn't look like it factors by grouping. If I group these two guys together and I factor something out, I'm not going to get the same thing if I group these two and factor something out. And there's no way I could just regroup so that I would have a common factor if I tried that. So at this point, if it doesn't look like it easily factors and it doesn't factor by grouping, I would start the process of finding factors by listing the possible rational roots of this polynomial equation. So we'll list those here. Here you take the factors of the constant term and you divide by the factors of the leading coefficient. The factors of the constant are the factors of 18. The leading coefficient is an implied 1. And there are a lot of factors of 18. So we could use plus and minus 1, plus and minus 18, plus and minus 2, and plus and minus 9, plus and minus 3, and plus and minus 6. 4 doesn't work, 5 doesn't work, and then we're back at 6. So we actually have 1, 2, 3, 4, 5, 6 times 2. So 12 possible rational roots in the numerator. And we're dividing each of those by plus or minus 1. So it ends up just being 12 possible rational roots of this equation. So let's list those over here. So you've got 1 and negative 1, 2 and negative 2, 3 and negative 3, 6 and negative 6, 18 and negative 18 as the possible rational roots. And then what we're going to do is we're going to try roots on this list until we find one that actually is a root of that polynomial equation. And then once we have a root, then we can find a corresponding factor. So that's the plan. And our equation was, let's see, m cubed minus 4m squared minus 3m plus 18. I want to make sure those signs are correct. Yes, the signs are correct. Okay, so I think I want to try m equals 2. So I'm thinking maybe 8 minus 16, 8 minus 16 minus 6. Well, maybe that'll work out. So maybe not. So I'll try m equals 2. I was trying to do the arithmetic in my head. So, you know, it's better just write it down. So I have 8 minus 16 minus 6 here plus 8. So this 8 plus 18 is 26. And then this is also 26, and that equals 0. Awesome. Now, if you tried m equals 1, it wouldn't work. M equals negative 1, it doesn't work. And I actually tested those possible roots in my head first before I chose m equals 2. I just said, well, if m is 1, it's going to be 1 minus 4 minus 3 plus 18. It's not 0. Negative 1, so that would make that a negative 1 and then a positive 3 and then a negative 4. I'm like, no, that's not going to work either. So that's why I skipped those two and went to m equals 2. So we tried roots from the list until we got one that equaled 0. That's great. That means that m equals 2 is a root. And if m equals 2 is a root, then m minus 2 is a factor of the polynomial. That's just a fact about polynomials. Since m equals k is a root of the polynomial, then m minus k is a factor of the polynomial. So I know that this cubic polynomial is divisible by this linear polynomial m minus 2. In order to show that it's divisible by m minus 2, we need to divide them. Well, not to show that it's divisible by m minus 2, I'm sorry. We need to divide them in order to factor out that m minus 2. I know it can be factored out. So this is going to be equal to some quotient where that quotient is just a single polynomial. Okay, so we're here now, and we want to find the quotient. And one way we can find the quotient is using synthetic division. So you take the factor m minus 2, you set that equal to 0 and solve for m. You get the corresponding root, which we know was 2. Then you list that polynomial in the numerator in descending powers of m, with the highest power first. Make sure you don't have any missing terms, and we don't. We've got an m cubed term, an m squared term, an m to the first term, and a constant term. So we list those coefficients over here. And then you bring down the 1, you multiply, you put that there, and then you add. Multiply and add. Multiply and add. Uh-oh. Looks like this is not a root after all. I must have made a mistake somewhere. M cubed minus 4m minus 3m plus 18. And we have this. This works out. So this actually is a root. So I must have made a mistake here. Bring this down, multiply, and then we add. Multiply, -4, and then we add. Multiply, and then we add -4 over here. Having trouble finding my mistake. I just caught it. I made an arithmetic mistake in my head. I don't know how I did that. I said that -16 minus 6 was -26, and it's absolutely not. That is -22. So that is not equal to 0. M equals 2 is not a root. Sorry about that. That happens sometimes. So let's try m equals -2. We'll have -2 cubed minus 4 times -2 squared minus 3 times -2 plus 18. We get -8 here, minus 4 times 4 plus 6 plus 18. Okay, 18 minus 8 is 10. negative 16 plus 6 is negative 10, so this is going to be 0. Or you could say this is negative 24, and that's positive 24, and we get 0. So m equals negative 2 as a root. I don't know how I made that arithmetic mistake earlier, but I did. This is when I wish I was in class so you guys could correct me when I make a mistake like that. So m equals negative 2 as a root. So that means m equals 2, or m plus 2 is a factor. And that's good. When I did the long division over here and I got that remainder of 4, that told me that I did something wrong. That's a very good sign. So if that ever happens to you, if you end up with a remainder other than 0, then you know that that can't be a root if you've done this correctly. And if you've done this correctly, and you said earlier that this was a root, but it's not, then something went wrong up here. And that's how I found my mistake. So we've got this guy is a root, which means this guy is a factor. So that means our polynomial, m cubed minus 4m squared minus 3m plus 18 is equal to this factor m plus 2 times some quotient, where the quotient is this divided by this. In order to find that quotient, I'm going to do the long division, or not the long division, the synthetic division. So you set the factor equal to 0 and you solve for m, that's the corresponding root of negative 2. You list the coefficients of this polynomial over here. You bring the first one down, multiply and add, multiply and add, multiply and add. That's good. I get a 0, which is what I was expecting. So this shows that m equals negative 2 is truly a root, and the quotient is a second degree polynomial, because you take a cubic polynomial and you're dividing out a linear polynomial, so the power goes down by 1 to a second degree polynomial, and it ends up that this cubic polynomial is m plus 2 times this expression here, it's going to be a quadratic polynomial with these coefficients. So we'll have 1m squared minus 6m plus 9. And that factors further to m plus 3 times, or excuse me, m minus 3 times m minus 3. Because negative 3 times negative 3 gives us positive 9, and negative 3 plus negative 3 gives us a negative 6. So this is m plus 2 times the quantity m minus 3 squared. And that's equal to this cubic polynomial over here. So our characteristic equation can be written this way. And we've got a repeated root and a distinct real root. So our distinct real root is negative 2. And our repeated roots, we'll call them m2 and m3, are both equal to 3. So the first one is, let's see, what was the variable? It was an x. So our first solution is x to the m1, so that's x to the negative 2. And our next solution is x cubed for this one, it's x to the m2. And the third solution can't be x to the third because that's already this solution. In order to get a third linearly independent solution, we've got to multiply this guy by an x. So we've got two solutions that go with this repeated root because it's repeated twice. Okay, now that's enough to write down the general solution. It was a third order differential equation. So we get c1y1 plus c2y2 plus c3y3, which is c1 times x to the negative 2 plus c2 times x squared plus c3 times x. This should be x cubed. c3 times x cubed times natural log of x. And this will work for x on the interval from 0 to infinity. So we're using synthetic division to find that quotient. And I actually did that down here. And then we factored the quotient as much as possible. Then we solved for m1, m2, and m3. Then you have solutions y1, y2, and y3. And then the general solution is C1y1 plus C2y2 plus C3y3, and it's on some interval I. Okay, so that was our example of repeated real roots. In the next example, hopefully we'll see some complex conjugate roots.